Okay, let's begin today. So this week we'll cover physics-informed machine learning and physics-informed neural networks. So for the aim of this lecture this week, we plan to cover basically what's physics exactly is, well, sort of. Also, how you can do physics-informed machine learning and what's a physics-informed neural network is, as well as how this relates to like loss functions and other machine learning and deep learning concept we learned about like last week. And we also see some examples from for forward or inverse problems as well. All right, let's get to it then. So what is physics exactly? Well, physics is many things. And in fact, you can probably take a whole degree to learn about physics. But what I would say is that physics, to me at least, is like the study of the fundamental laws of natures. And oftentimes, we can describe these laws via some mathematical equations. More specifically, we can model these via equations that involves derivatives. So this is what you will call differential equations. So basically, for a rough outline what differential equations are, there are mathematical equations that describe some kind of law of nature or some kind of systematic behavior. These often involve derivatives like you expect in the names, and these describes the interactions between the variables in the system. So here's one common example. Here, we can model the bounce of a spring via this so-called differential equation here. Here you can see that there's some kind of force term, like you see from Newton's law of motion. There's also some kind of friction term, and as well as a spring term. These spring models are very common throughout physics and can be used to model many kinds of different phenomena, such as quantum effects, or some more interesting like resonance effects that you can see on like bridges sometimes if they're designed that way. And for another more complicated example, we have waves. Waves tells us how stuff basically kind of spreads out over space and time. And different from the previous example, involves two kinds of inputs, space and time. These here, we can see one kind of an animation of waves taking place. Here we see a seismic wave from an earthquake being released through the surface of the earth through different kinds of material interfaces in the rock, where the colors represent like different kinds of rocks in the surface. And we can use this wave equation to model the strength of the wave as it goes through the earth, basically. So those are just some of the two common kinds of equations and that we're going to be considering for the lecture today. Any questions? Okay. So solving these differential equations is a pretty difficult challenge. They can often require some specialized expertise or takes some really large computers and resources as well. This industry is what you call like scientific computing, and it's on the order of like $50 billion last I checked. And this is used in like many industrial applications like aircraft design, forecasting, and some more methods I can't list off the top of my head right now. Now, one common hope for people or practitioners that we can hopefully maybe kind of use some kind of machine learning method like deep learning to kind of solve the equations for us. and hopefully they'll come out like faster or maybe a bit more accurate out in the end. But more specifically, we can try to use a neural network to model the solution of these underlying physical equations. To do this, we first have to collect some data, pairs, like we have like the inputs here and like the unknown quantities. This could be like the amplitude of the spring, like I talked about earlier, or the strength of the wave. And this is required so we can do supervised learning on the neural networks. Because if you recall, basically what a neural network does, it takes your inputs and basically processes it through some parameters to compute the output and the end. This output is just a prediction of the underlying true output, and we then have to compare it through the training data that we collected beforehand. And then we have to optimize the neural network out and in to figure out these parameters. After the training process, we can then do predictions. So what happens when you try to do this training and predictions? Well, it's a bit finicky. For one example, with like the spring, you can see that during the training of this of the spring, we can see that the neural network is having difficulty to extrapolate beyond the training data, and that it doesn't fit the underlying sinusoidal behavior that you expect from a spring. This is and this is pretty problematic because this is a pretty simple example, probably one of the most simple models of physics you can come up with. And then if you try to even attempt the wave equation here, we have a reference finite difference simulation that people in scientific computing would commonly do. And here we have the neural network prediction. Initially, the predictions start off pretty accurately for the first two like time steps, but then afterwards you can see it basically lose all the fine-grained detail in the simulation out in the end. So this is pretty problematic. We wouldn't want this to happen when we try to basically design any other systems on top of these using neural network methods. But is there any way we can solve we can improve the underlying physics abilities of these neural networks? And these direct approaches just aren't working for us right now. Any questions? Yes?
So for the damping oscillator, what if we increase the training size or the compensate of the number?
Well, that's a fair approach, but that's basically kind of like doing like regular machine learning, where you just basically increase your data and your model size. But at that point, it starts to get possibly pretty really expensive, because sometimes then you have to buy more GPUs out and then you have to go out in the field more often to collect even more data. Sometimes the data set that you have is quite limited and you can't even collect more data afterwards. Like you can't collect more data in the past, like in weather forecasting, you can't collect any more data. You can only collect future data, but you can't do it. You can't really increase the rate of data collection at all. And even if you try to increase the model size, you often try to avoid bigger models in these scientific applications because you want your models to be simple in the end. You want them to kind of basically reflect the underlying physics. Okay. Any other questions? Yeah.
So basically, you will offer just like linear map systems. A lot of physics problems are fundamentally we just change somehow if you live in the system and all the physics with that Taylor expansion and
You can try to do Taylor expansions, yeah, but it's a bit it can be done, yes, but that's well, that's kind of basically the idea roughly that we're going to do now with physics-informed machine learning. Roughly. Okay. So physics-informed machine learning and neural networks. So last week, we saw how we can improve neural network performance on scientific tasks by modifying its architecture using operator learning, where we basically change the network structure and the layers that we use in the design of the model. This is like the Fourier layers that we were talking about last time, or like the convolutional layers that's been done in like image processing. But if you think about this a lot, this doesn't really capture the underlying law that the data follows. It only captures how the high level details of the data, whether it is like just like a kind of an image versus a sequence or just a bunch of numbers. So is there some kind of better way to capture the underlying physics in like these models? And the answer to that is yes. One approach that we can take instead is that we can change the loss function that we use to train the neural networks, because these loss functions are important, because during training, this is what informs the network to basically update the parameters and make the predictions in the end. So what we're going to do now is we're going to add a loss function just for the physics. And so for a bit more detail about that, we basically have like the outputs of the neural network that we have from before, and then we start computing the derivatives of those outputs with respect to the inputs. And then we can match this up to the equation, to the underlying differential equation that the data follows, and try to minimize the differences out in the end. So what I mean is that we have like this traditional like supervised loss that we have from normal deep learning. And then if we know that the data is like follows like this kind of like harmonic equation here, we can just add that onto the loss function as another term. So here we can just, since we know that if the physics are satisfied, then the differential equation is equal to 0. But just like how the neural network is just only an approximate solution of the underlying outputs, we can just minimize the difference, and so which is what we do here in the physics loss. Yes.
Okay, so you're multiplying the physics loss with a hyperparameter lambda, which I presume is to kind of like distribute the weight between supervised loss and physics loss.
Yeah, it kind of represents the strength of like how much physics we want out from the model.
Question becomes, what if application is like really common, right?
Yeah.
And we just cannot run this over and over and over again to get a good value for a hyperparameter lambda. Then what do we even do? Like, is there like a general rule of thumb to choose the lambda initially, assuming that we don't have the computation capacity to run this neural network over and over again to get a good neural network by trying out different numbers?
That's a good question. So what you can do in that case is that you can, the special thing about this physics loss that you might not notice is that the summation happens over a different index compared to your supervised loss. And the reason is for that is for supervised learning, you need both the data inputs and also the outputs to compare. But when this physics loss, you only require the inputs to the differential equations. You don't need to go out and record any of like temperature readings or strength readings at all. So in some ways, this is a bit easier to do than supervised learning. And in that case, you can just scale down your data set if it's too hard to compute. or you can try to do some clever optimization techniques to determine what the value of your lambda can be in that place.
What we do techniques.
There's some fancy work where you can just alternately optimize the loss first and then take the optimal value of lambda and then keep on iterating that process over and over again. But that's a bit out of scope. There's some other techniques to do some kind of transfer learning first, where you start off with your with just learning using just the physics loss alone, and then switch to a supervised loss if you have the data. It's depends on like how difficult your physical models are, but yeah.
Okay, so you said you can first start with a neural network that only computes the physics loss, right?
Yeah.
But the physics loss has a neural network embedded in it.
Yes.
So we would need some initial data to actually even have that neural network to give us the results for the physics loss. How would it?
You can just basically just generate like your like input locations out of thin air, basically. Like it's kind of like you want to say you want to install like a satellite like the North Pole. You can kind of like simulate like the effects of what that does by just placing one at like 0 longitude and 0 latitude and just figure out how that would behave. And since you know like the temperature follows this certain kind of law of physics, you can, if you manage to optimize that physics loss good enough, then you can be somewhat confident that your model is behaving the way it should be behaving. That was one of the points I'm going to cover like near the end of this talk, but we can go to there now, I guess. So yeah, a bit more on your question. This physics loss is what you will call like a unsupervised regularizer. So what it does, it adds prior physical knowledge into the neural network during training. And because if you look at the equation here, you can only see like there's no outputs appear in the data that's required to compute this loss function at all. So you can just test your physics loss everywhere on the domain without even having to record like temperature values, velocity values that come out from these like differential equations. And doing that, you can do some predictions out and end. So here, I'm technically jumping the gun. We can add physics loss training locations everywhere on the domain. This is separate from the training data, which are paired together with like the output results, but we can still optimize the neural network with both in tandem to get some much better behavior out in end. Does this make sense? Yes?
Physics model, it's like you see the differential or like equation that solves the differential equation, and then the loss function kind of applies it.
Not exactly. When you generate the data for your physics loss, that's kind of like your initial conditions. And then when you optimize it, it just improves the quality of the model. Okay. Yes.
So one thing to notice is, in this PINN application, you're seeing training steps just going through the roof, right?
Yes.
Like it's going
Yeah.
all the way up to like 20,000. And for the naive neural network, we like.
It only took like 1,000. We only stopped after 1,000 because it's just bad. And there's no improvement.
When you take like this screenshot of this at 1,000 steps, it's still haven't like made any progress, right? So why is that? Like why when we add the loss function, we don't get the same amount of improvement at the 1,000th step. Like,
So,
why is this a little slower in that regards?
so when you add this physics loss in tandem to your supervised loss, it makes your training much more difficult from an optimization perspective. And another comment is when you use like a specific choice of optimizer to do this optimization, that has a major effect on your speed of convergence. So in this example, we use a more machine learning based optimizer called Atom, which was developed here at U of T for training neural networks. It's one of the most cited papers in this century, like 100,000 citations. But if you were to use like a different optimizer that's more suited for like scientific applications, then you can get much faster training in the end.
Are we use of those optimizers? And like,
Those are like,
are most-
those are called like second order optimizers. Like they're like something you call like Newton's method. But that's a bit more prohibitively expensive. But if you want a more efficient second order method, you have something like LBGFS optimizer, which is named after like the four people that kind of designed it. I can't remember like the full names off the top of my head, but it's like LBGFS. So yeah. Any other questions? Okay, so where were we? So yeah, basically you just have your like your neural networks, and then you can take derivatives with respect to the outputs to kind of calculate the derivatives corresponding to the differential equation and try to match up the behavior in the end via learning the differences and trying to minimize the differences out in the end. So a bit more details about this process. You might ask, how do we exactly compute these derivatives out in the end? Like this second order time derivatives or this term as well. Basically, what you can do is that a machine learning has progressed so much partly because of auto differentiation. And what auto differentiation does is just lets us take derivatives basically anywhere. Here's a bit more explicit example of how you'll code up the physics loss. Now, I won't explain the whole process of the code to you right now, because that's more the topic of the coding tutorial next week. But basically, you just have to like add these two options, and then you can just tell your machine learning framework to take the derivative, and then it just works out, and then you just add like your loss functions together with your data and your physics loss, then back propagate and then update the model, and then you keep on repeating this over and over again. Make sense? Okay, so once you add this physics loss, we can see substantial improvements to over a neural network approach. Here in this third column, we see the pins output, the neural network plus the physics loss, and we can see it's nearly identical to the ground truth of the finite difference method throughout all time scales. And we also see this in the training behavior as well with the spring equation that I showed you earlier. So a bit more to elaborate a bit more about the unsupervised abilities of the physics loss is that because it's unsupervised, we can technically not record any training data or just have a very limited sample of training data, like just a few dozens. And we can have just instead millions of physics loss training points instead to help train our model. This greatly helps improve model development out and then, because you don't have to worry about data collection as much as you would have to in like the traditional machine learning methods. So yeah. And these unsupervised learning methods are also prevalent in other fields of machine learning, like computer vision and language processing as well, which is why it kind of spearhead those other fields ahead a lot. Okay, any questions? So this has been pins applied to board problems where we just try to predict something out and then like predicting some output of your neural network, but or some differential equation. But you can also use pins to do inverse problems. For example, in the spring equation, you might not know what the friction coefficient is, this mu here, but you know that when you were doing your measurements of the data, that friction was observed, and you're trying to estimate the friction coefficient out in n, even though you didn't directly measure it. So this is like an inverse problem per se. And basically what you can do is you can use the machine learning frameworks to help you out and determine the unknown value for mu. So here we can see that even when we have like the noisy input data, we're still able to estimate the true underlying friction coefficient out and then after enough training. Okay. So this is why and this is only possible due to the unsupervised physics laws. Because if we didn't have it, we can't infer or kind of inform the model like how it should behave out in the end. Any questions? And for another approach, we can also do some shape optimization. For example, we can solve the brachistochrone problem and solve its variational equation and we basically end up with like the brachistochrone curve after enough training out and then. This uses more ideas from like the automatic differentiation, which we will be covering in the next coding tutorial next week. Any questions? So yeah, that's basically what I have this week. It's technically not too much since I kind of jumped the gun because you guys asked a lot of questions in the middle of it. But next week we'll cover how to actually code these models up more and how to do this in practice. Sounds good? Okay. Yeah. Right. See you guys next week.